Okay, we're going to go through a script that is going to create a sample data set, a simulated data set, but we're going to add a little feature here. We're going to add a new variable that's going to represent some of our treatment group who have attrited from the sample, who have left the sample, and so their outcome is no longer observed. So we'll do that, and then we'll do a little bit with that data set that we create. So as before, we start by clearing our data set, so clearing the environment. We load our packages. So we have Tidyverse, the sandwich package, and Stargazer to display regression results. We will, I'm not going to set a seed here. Normally we would set a seed so that every simulation we'd always get the same results. But one of the things I'm going to do here is show you that if you repeat the simulations, you'll get different results and how those results will vary. So we won't set the seed here. So I hashtag the set seed command. Let's start with a data set of 400. So it'll be pretty simple. So we have 400 here in our environment window. We're going to create a very simple data frame. So a treatment variable that's going to be 0, 1, an urban variable that's going to be 0, 1, a female variable that's going to be 0, 1. And remember, we can sample from 0 and 1, or we can just use the R binomial function to create a 0, 1 variable. Another variable called minority, 0, 1. Education, which will be sampled from 3 to 8, 3, 4, 5, 6, 7, 8. Uniform distribution, so every number has the same probability. And then age, we'll sample from 18 to 60. And again, each one will have the same probability. So we create that data set. Our n is 400, so we're going to have a data frame. We call it df. Our data frame has 400 observations of these 6 variables. We click on the blue button here, and we see the 6 variables. We see that age is in the right range, education's in the right range, and the other 4 variables are all dummy variables, 0, 1 variables, as we indicated, right? So that's our data frame. We can add an ID variable. We don't have to, but we're going to add an ID variable here that's just the row number. Let's take a look at what the mean of female is. So 0.45, and indeed our female was 0.45. Let's run it again, though. And now we get 0.43. Let's run it again. Now we get 0.42. Let's run it again. 0.45. Let's run it again. 0.46. So every time we run it, we're drawing random samples. So we're going to get slightly different values for the 0s and 1s. And even though our probability is a female is 0.45, because we're drawing random samples, they're going to be slightly different from that just by drawing a random sample. Sometimes they'll be close to 0.45, very close, or exactly 0.45, but sometimes they'll be a little bit further away. Just like flipping a coin, right? On average, it'll be 0.5 heads, 0.5 tails, but if you only flip a coin 10 times, you're not going to have 5 heads, 5 tails. Sometimes you have 6 heads, sometimes you might have 7 heads. That's the same principle at work here. So we have our we're now going to define a treatment effect. So we'll create a new variable. We use the mutate function, create a new variable called treat effect. If the treatment status is equal to 1, then the treatment effect will be 2.5, otherwise 0. So those in the treatment group have an effect of 2.5, others have 0. We can let's see the table. We have 184 who are treated, and that means we have 184 people who have 2.5 as their treatment effect, and the other people have 0. Now we'll create an outcome variable. So again, we use mutate to create an outcome variable. If the person is in the treatment group, then their outcome is 2 plus the treatment effect, which is 2.5 for them, plus 0.3 times female, 0.52 times education, minus 0.08 times female times education, plus some random variable. So that's our measurement error that'll be different for every person. So 400 observations, each one will have a different random component to their outcome. That's the measurement error, the random noise that we think about in our regression model. So let's create our outcome measure. There we have our outcome. We can do a histogram of the outcome measure, df $outcome. So there's a histogram, and we see that the outcome centered around 6 or something, 6 or 7, and ranges from -10 all the way up to about 20. So that's our outcome measure. Now we're going to create a new variable called attrit, and what we're going to do is we're going to say, suppose you had a really good outcome. Let's say it's profits or something like that. So you had really good outcome, you had really high profits, then you don't want to answer the questions anymore. So you attrit out of the sample. So we're going to say that if your outcome is bigger than the mean outcome and plus 1 standard deviation of the outcome, so it's sort of like out around here, the mean is around 6, say, so you're out around here, 1 standard deviation away might be 10. We can actually look and see what this value would be. I'm going to copy it and paste it right here. And we have to tell it that it's the outcome in DF. See, on the bottom, we were using Dippler, we're using the pipe. So we didn't have to keep telling it what DF is. But now we're doing it standalone. So we have to tell it that it's the outcome variable in the data frame. Oh, this is giving us, we just want to know what the mean is plus 1 standard deviation. There we go. And I was exactly right, 10.10. So that's the mean plus 1 standard deviation. So if you're above that and you're in the treatment group, we'll say that you attrit out of the sample. So how many are going to be attrited? Well, out of our 400, 48 are attrited. Remember, we had 200 in the treatment group, 200 in the control group, roughly. And so of the treatment group, about 50, so about 1/4 drop out. So the top 1/4 of the treatment group, those who have the biggest effects, are the ones who drop out. So now I'm going to create another variable called outcome old. That's going to be the old outcome. And then I'm going to change outcome so that if you're in the attritted group, if your attrit equals 1, then your outcome is going to be missing. And if you're not in the attritment group, outcome's just going to be whatever it was. So I'm going to have the old outcome and then the new outcome where it's going to be missing if you're in the attritted group. Now I'm going to run 2 regressions, one with the outcome that has the missing ones and then the other with the old outcome. Now what should happen, right, is since the treatment group, it's the top performers who we don't observe anymore, it should look like the treatment doesn't have a big effect. Right? Because those who are most positively affected by the treatment, they are no longer observed. So it should, only the ones in the treatment group who didn't have such great outcomes are left. So it should look like the treatment doesn't have as big effect. And how can we tell, what it should look like? Well, remember, we still have this outcome old there that I just created. So we can run the regression with that. That would be, suppose we did observe everybody, and then we can estimate the effect of the treatment. So let's go ahead and run that, reg 1, reg 2. And some reason something didn't work. Oh, I didn't run line 45. So let's run that again. And there's our regression results. And we see indeed, when we have the attritted there, so we only have 352 observations, treatment is no longer statistically significant, right? It's no longer statistically significant. If we hadn't had those people drop out, we would have observed a treatment effect of about 2.3, right? Close to the 2.5 that we programmed in when we generated our simulated data. So you can rewatch that. You can rerun this since you have the script yourselves. Let's do a couple little extra things here, just to something we can do when we think there's attritted data. We can check the bounds of our treatment effect by saying, well, let's suppose that if we think that the treatment group had a lot of attritters, let's then assume that we would have had just as many attritters in our control group and consider the 2 cases. Suppose all the attritters in the control group were the best ones, and then suppose all the attritters in the control group were the worst ones. So that's like a hypothetical. So we're saying, suppose that we also had a lot of attritting people attritted out, leaving the data set in the control group, and it was the best ones. Or suppose we had a lot of attritters in the control group and it was the worst ones who attritted. What then would we estimate as the treatment effect? So that's Reg 3 and Reg 4. And I'm going to use the correct standard errors here. Reg 5, why is it saying Reg 5? Oh, I see, Reg 5. We don't have a Reg 5 here. There we go. So we can see that our bounded estimates of treatment are from 3.8 to minus 0.63. So that's the range of estimates. So we see, by and large, we'd conclude from this that even with a lot of a treatment, our treatment effect is basically probably positive, since in the worst case scenario, it's a small negative number.